What is lurking at the very heart of our own galaxy? For the longest time, we thought we had it all figured out, but well, a new theory is challenging everything we thought we knew about the center of the Milky Way. So let's dive in and see what's really going on.
For decades, the consensus among scientists was pretty solid. You see, by watching the wild, looping orbits of stars near the galactic core, astronomers figured something with a truly immense gravitational pull had to be sitting there. They even gave it a name, Sagittarius A star, our very own supermassive black hole.
But what if that incredibly powerful, invisible object isn't a black hole at all? What if it's something we've been hunting for all across the cosmos, and it's been hiding right under our noses, right in our own galactic backyard?
Now, the whole reason we suspected some kind of monster in the middle in the first place comes down to one thing: gravity. We could see stars whipping around the galactic center at just incredible speeds. For that to happen, they had to be orbiting something with about 4 million times the mass of our Sun, all packed into a ridiculously small space.
So, the natural candidate, the obvious suspect, was a supermassive black hole. We're talking about an object so dense it's almost impossible to imagine. Its gravity is so intense that once you cross its boundary, the event horizon, that's it. There's no coming back. It seemed to fit all the evidence perfectly.
But there's a pretty big problem. As our telescopes, like the James Webb, peer deeper into the early universe, we're finding these supermassive black holes way earlier than our theories can comfortably explain. The big question is, how did they get so huge so fast, right after the Big Bang? This nagging puzzle has really opened the door for some other pretty wild ideas.
And that brings us to the challenger in this cosmic title fight. It's an idea that suggests the galactic center isn't a singularity at all. Instead, it might be a dense, massive core made out of a very particular kind of dark matter.
Okay, so this is where a key distinction comes in. Our standard model for dark matter, cold dark matter, is, well, kind of aloof. Its particles just phase right through each other, only interacting with gravity. But in this other model, self-interacting dark matter, or SIDM, the particles can actually bump into each other. They can collide. And that ability to interact and transfer heat allows it to behave in a completely different way.
So how does this stuff form a galactic core? The process is called gravithermal collapse. At first, the SIDM particles collide, and that transfers heat outwards, forming a nice, stable core. But then, as the core keeps losing heat to the outer regions, it starts to shrink and get denser. This kicks off a chain reaction, accelerating into a runaway collapse where the density and temperature just skyrocket. This continues until you're left with an incredibly dense object right at the center of the galaxy, an object massive enough to perfectly mimic a black hole.
We're really at an incredible crossroads in cosmology here, with two really powerful theories competing to explain what's going on in our own galaxy. If you're finding this whole journey into the unknown as fascinating as we do, go ahead and hit like and subscribe. It really helps us make more stuff just like this.
So, we have two theories on the table: the classic supermassive black hole and the new contender, a dark matter core. How in the world do we decide between them? Well, it turns out the answer is to watch the stars.
And they're not just watching any star. Astronomers are zeroing in on one star in particular, named S2. S2 is special because it has this super tight 16-year orbit around the galactic center. Its path is extremely sensitive to the gravity of whatever is sitting there, which makes it the absolute perfect probe to test our theories.
And this is where the mystery gets really good. When we plot S2's observed orbit against the predictions from the black hole model, it's a beautiful match. Fits like a glove. But then, when you plot that exact same data against the dark matter core model, it also fits. I mean, it fits remarkably well.
So, why can't we tell the difference? The problem isn't with the theories, it's with our data. Our measurements, as incredible as they are, just aren't quite precise enough yet. You see those little vertical lines on the data points? Those are error bars. They represent the tiny bit of uncertainty. And right now, both of these theories fall comfortably within that wiggle room. This leaves us in a really fascinating and honestly a very exciting state of uncertainty. We've got the long-established king on the one hand and a seriously powerful new contender for the throne at the center of our galaxy.
Okay, let's just summarize this head-to-head. Theory 1 gives us Sagittarius A star, a singularity with an event horizon, that point of no return. Theory 2 gives us a dense sphere of self-interacting dark matter, which has no event horizon. And as we've just seen, the S2 star's orbit, well, it fits both models perfectly right now.
It really is the established consensus versus a very compelling new challenger.
So, how is this finally going to get settled? Well, the answer is probably hidden in measuring the very, very subtle precession of these stars' orbits. You can think of it like the tiny, slow wobble of a spinning top. A black hole and a dark matter core should cause slightly different wobbles. It's a measurement that's just beyond what we can do today, but it's exactly what the next generation of telescopes is being built for.
For now, the heart of the Milky Way remains a place of profound mystery. And it's a powerful reminder that science is always a process of questioning. It shows us that sometimes the greatest discoveries are hiding in the places where we dare to challenge the things we think we know for sure.